Okay, good evening, everyone, and welcome to the second of our virtual alumni events. My name is Richard Harrison. I'm the current head of department in Earth Sciences, and it's been a hell of a year, as I'm sure you've realised. It's just coming to an end, and we're very grateful for that. And it's been a shame that we haven't been able to invite you all to the department in person for any of our normal events. So instead, we've arranged these virtual events, which give us a really good chance to share what we've been up to, what our staff and our students have been up to. We've got a nice lineup of speakers for you today, including both staff and students. So a few housekeeping notes. So your microphones and cameras will be off throughout the event. We've got two sets of speakers, and after each one, there'll be a chance for you to submit your questions. You can submit those anytime during the presentation using the little Q&A button down at the bottom, and we'll do our best to address as many questions as you can. So do send them in. We really like to hear your questions after each of the presentations. And we are recording this event. Our aim is to put this out on our YouTube channel later on for those of you who couldn't make it tonight. So just so you're aware of that. So yeah, without much further ado, I'm going to hand you over now to our Master of Ceremonies for the evening. I'm sure you all know Nigel Woodcock. Over to you, Nigel.
Thanks very much, Rich. Yes, hello everybody. So it's my pleasure to get things started and introduce Ed Tipper. Ed is homegrown talent. He was an undergraduate in Cambridge from 1998 to 2002. He stayed on to do a PhD and then went on a partial sort of European tour, postdocs in Paris, then in Zurich at ETH, and then back for a year's NERC research fellowship in Cambridge before getting a job, a lectureship in St Andrews for 3 years. And in 2004, we attracted him back to Cambridge, which is where he's been ever since. He joins a long line of eminent geologists by being a fellow of St John's and looking after John's students. So over to you, Ed.
Thanks very much, Nigel, for the introduction. And it's an absolute pleasure to give a short talk this evening about some of the research that I've been doing over the past year or so, or over the past few years, since I started here in Cambridge. And when I say my research, actually, it's not really my research at all. It's the research of a team of people that I've been lucky enough to work with. Postdoctoral researchers, but also undergraduates, undergraduates who I've been fortunate enough to have come in the field with me on their Part 3 projects or their master's projects, their 4th year projects, and really travel around the world and collect a whole series of samples, which I'm going to be talking to you about this evening. Now, my research is really all about the long-term carbon cycle and Earth's long-term carbon cycle. And the textbook view of the long-term carbon cycle is there are volcanic emissions. There is volcanic degassing of the Earth, releasing carbon dioxide into the atmosphere. And this sort of begs the question over millions of years, over geological timescales, it begs the question as to why our planet didn't turn into something like Venus, like we have here, where there is a runaway greenhouse effect on Venus. And of course, the textbook view of this, the view of this that has sort of prevailed in textbooks really for the best part of the last 40 years, is that silicate weathering, i.e. the dissolution of silicate rocks, the dissolution of calcium-bearing silicate rock. So this would be an example, a sort of a schematic example of a calcium-bearing silicate, a feldspar in this case. The idea would be that you take carbonic acid, so carbon dioxide dissolved in water, dissolve a silicate rock, and over a long time scale, you transport calcium ions to the ocean, and you form calcium carbonate. And in doing so, the overall product of this reaction takes carbon dioxide out of the atmosphere and stores it in the planet's largest reservoir of carbon, except the core, which is limestone. And that's where most of our carbon resides. And it's been thought that this is very simple.
Are you meaning to share your screen? You need to be sharing your screen. I think you're referring.
Oh, am I not sharing?
No, we're not seeing anything. Sorry.
Apologies, I thought I was. Thank you, Nigel. Why am I not sharing?
It's just dawned on us that we're not seeing the pictures you're describing.
Yeah, no, thank you. Thank you for pointing that out.
Oh, that's better. Yeah, you're fine now.
Is that right?
Yeah.
Okay, thank you, Nigel. Apologies for that. So yeah, a very simple schematic reaction, which many of you, this has been in the textbook view for decades. And so this has built up a reservoir of limestone. Now, of course, when it comes to mineral dissolution, one of those things that's then going to redissolve is limestone itself. Calcium carbonate will dissolve, and it will dissolve itself. And the canonical view of this has been that this is carbon neutral and has got no effect on atmospheric carbon dioxide over millions of years is what we're talking about. So it's obviously very different, short climate timescales. But this sort of view is changing. And this is something that my team's been involved in. And I want to sort of try and illustrate two examples of how this view has been changing, this textbook view that's been around for the last 40 years. And one of the reasons this is changing is this idea that sedimentary pyrite, which you can hopefully see here in this picture, sedimentary pyrite, when that dissolves, when that oxidizes, it effectively rusts. And that process of oxidation of pyrite, it generates sulfuric acid. And that sulfuric acid can equally as well dissolve calcium carbonate. That sulfuric acid dissolves calcium carbonate. And that reaction releases carbon dioxide back to the atmosphere. So H2SO4 releases calcium carbonate back to the atmosphere, or releases carbon back to the atmosphere. And this is something that we're, as geologists, have actually been familiar with for decades, but as geochemists haven't particularly addressed this. This is actually a photograph that I took yesterday on an undergraduate field trip at Ketton Quarry. We took our undergraduates yesterday to Ketton Quarry to make up for some of the lack of field work that we've been able to offer them because of the pandemic. And I was reminded of this process of pyrite oxidation and limestone dissolution by this very photograph, where we've got, this is a chunk of limestone from one of the formations at Ketton Quarry in Lincolnshire. And this blue heart in the middle of this chunk of limestone is where the pyrite hasn't, disseminated pyrite that's present throughout this limestone was not oxidized, but this yellow ochre rim that we've got on the outside is being caused by iron staining, iron oxide staining, where that iron was liberated from pyrite. And when that pyrite was oxidized, not only did it change the color of the limestone, of course, it did something to the limestone that I think we're all abundantly familiar with, causes that limestone to effectively fizz or effervesce and, of course, release carbon dioxide back to the atmosphere. And one of the things my group has been interested in trying to figure out is how much is this going on at a global scale? How much is this process going on at a global scale? And how much does it seek to offset carbon dioxide consumption through silicate weathering? And so I'm an isotope geochemist. I've been measuring isotopes since my PhD, really. And one of the sort of intuitive questions you might want to ask is, well, surely we should measure sulfur isotopes to try and figure this out. The key problem being that we need to try and figure out the origin of sulfate. Sulfate can come from two things. It can come from gypsum dissolution, and it can come from pyrite dissolution. And it turns out that sulfur isotopes are actually rather complicated and are not much use. They don't actually help us solve the problem because they show a huge global variation. So sulfur isotopes, although they'd be the most intuitive thing to turn to, they don't actually help us solve the problem. But actually, oxygen isotopes do, because when you oxidize pyrite, you take iron disulfide, pyrite, and you turn it into sulfuric acid. And when you do that, you generate sulfate. And when you generate sulfate, of course, you combine oxygen with sulfur, and we can trace the origin of that oxygen. Now, of course, I'm not going to go through all of the details of how we do this in this talk, but I'm going to give you an example of a place where we applied this logic and show you what the results are. And the example that I want to talk through is a major river that we've been looking at in Southeast Asia. And that major river is really one of the major catchments. So this would be the outline of India here. And we're looking through Southeast Asia through this region here. And this is the Ganges-Brahmaputra catchment. This is the Irrawaddy catchment through Myanmar, the Salween catchment that also exits into the sea in Myanmar. And we've been working on the Mekong, and it's the Mekong that I want to talk through this evening. And this is just a geological map of the Mekong Basin. It's got incredibly diverse geology, a very complicated and rich geological history. Since 2014, we've been sampling the Mekong. These are just some little snapshots of us sampling the Mekong from the very top of the catchment, right on the edge of the Tibetan Plateau, all the way down to the mouth, sampling river waters, river sediment from this catchment over many times with PhD students, with postdocs, and with undergraduate students who've come along the trips. Been quite a number of adventures. And what we've done with those samples is we've measured a whole series of things on them. And I don't want to talk through these plots in any great detail. This is an isotope cross plot, and it doesn't really matter what the axes are. What matters is what we're looking at here. These are our water samples that we've measured, that we've collected and that we've measured. And what we're able to do is we're able to infer different chemical end members. And so this would be a gypsum end member, and this would be a pyrite end member. And essentially, if our water samples plot close to this pyrite end member, we have a large amount of sulfuric acid generation. Whereas as a contrasting example over here, if our water sample plots close to the evaporite end member, to the gypsum end member up here, we haven't got much pyrite oxidation and we haven't got much sulfuric acid generation. And we can figure this out. We can work out the fraction of sulfate that's generated from sedimentary sulfate dissolution, so evaporite dissolution, as compared to pyrite dissolution. And the consequences on the carbon cycle are really important. Now, as I said, I'm not going to explain any of the modeling, any of the detail as to how we do this. Suffice to say that quite a lot of things go into it, not least, for example, maps of the Del 018 of precipitation or of water throughout the basin. So we have a map of oxygen isotopes throughout the basin. We have maps of the total amount of precipitation throughout the basin as things which feed into these calculations. And we're able to do these calculations for every tributary where we were able to collect a sample, which turns out to be a lot of tributaries. All of these samples here, we were able to figure out the amount of sulfuric acid weathering, and that enables us to work out quite an important thing across the whole basin, and actually to generate maps of the total amount of sulfuric acid weathering across the entire basin. And maps of all sorts of things here, but the key ones that matter are this panel here, where the dark colors indicate very large amounts of sedimentary sulfide oxidation. And so that's the fraction of sulfate which is being derived from pyrite oxidation. That's quite an important thing, but that needs to be combined with how much is actually going on in each of those catchments. And so this final panel actually gives us the total flux of sulfuric acid generation in each of those subcatchments. And when you add this up, when you tally up that total effect on the carbon cycle across the whole basin, it reduces the total silicate weathering flux by about 70%. So quite a significant result. This silicate weathering flux, this thing that we thought was going to be the major effect on removing atmospheric carbon dioxide, well, our work has showed that that's being reduced by 70% in this one major catchment. And I should say it's not a negligible amount of carbon that we're talking about. The amount of carbon that's being transferred through the Mekong River every second in the peak monsoon season is about 350 kilograms per second in the dissolved load alone is being transferred through the Mekong River. which is about enough to drive several thousand kilometers every second in an average family-sized car. This is a lot of carbon that's being transferred in these river systems. And we're showing that the amount removed from the atmosphere is much smaller than it previously was. And that's not the only thing that's going on that we've been working on that seeks to reduce this overall silicate weathering feedback. We've also been looking at interactions between the river water and the dirt or the sediment that is carried in that river water. And one of the major interactions that we've been looking at is something called cation exchange. And this is something that soil scientists have understood, that people that work on aquifers have understood, but geochemists working on rivers have totally neglected. And the idea of cation exchange is that particles, in particular clays, being transported in the river sediment have got charged surfaces. They've got negatively charged surfaces, and that can attract positive charges from the river water, such as calcium or sodium, which can attach themselves to the clay. And which positive charge is going to attach itself to the clay depends upon the environment in which the clay is on. And so this effect is going to be important in rivers with a high sediment capacity. This here is the Mackenzie River discharging large amounts of sediment into the Beaufort Sea in northern Canada. And you can see large sediment plumes going into the ocean here. And as that sediment goes into the ocean, sodium is the dominant cation in seawater, and sodium becomes the dominant ion on the exchange pool. Sodium replaces all other ions on the surfaces of clays as those clays go into the oceans. Now, subsequently, what happens many millions of years later, that sediment becomes uplifted and becomes exhumed and becomes emplaced as a mountain belt at some point as a sedimentary rock, the kind of sedimentary rock that as geologists, we might go and map in the field and look for. We might go mapping shales, for example, in the field. I can think of numerous undergraduate field trips where I spent time looking at shales. If those shales were deposited in marine conditions, then the exchange sites in those shales become saturated with sodium. And that sodium during modern chemical weathering gets released into a modern river water, and those exchangeable sites get replaced with another ion. Now, this origin of sodium matters because most geochemists use sodium to estimate the total amount of silicate weathering that happens in modern environments. They use sodium as a proxy for silicates. And the reason they use sodium is that it's a relatively simple ion to use. Calcium, for example, is derived from both carbonate and silicate, and so it's hard to work with. Sodium can only come from either silicate or salt, and salt's very easy to correct for. And so I'm going to put up a very complicated diagram, but there's only one thing you need to know about this diagram. You need to know that red equals bad for carbon consumption and green equals good for carbon consumption. And so this is a diagram. On the x-axis, we're looking at suspended sediment concentration. On the y-axis, it doesn't really matter. It's the total amount of sodium, the plausible amount of sodium that could be on the exchange pool. And this is something that we've been around the world, or around several of the world's largest rivers. We've built up a very large collection of suspended sediments. I think it's fair to say, I think we've collected the largest collection of suspended sediment on the planet out of all of the labs in the last 7 years or so, to try and measure this effect and try and figure out what's going on. And this particular example is from the Salween River. And this bar in here shows our average suspended sediment in the Salween. And you can see where our average suspended sediment plots, it significantly intersects this red band in here. And in fact, if it's completely red, it means that the total amount of silicate weathering is actually zero. There is no silicate weathering at all that can be deduced. And so what we've done is we've mapped this out at a global scale. And so this is a global map of the reduction in the silicate weathering flux, which we published late last year or early this year. And again, red colours show a substantial reduction in the total silicate weathering flux. So for example, our work is suggesting that the silicate weathering flux in the Mackenzie is actually about 70% lower than previous estimates. In the Yellow River or the Huanghe, it's about 100% lower than previous estimates. So essentially reduced right down. And so we have a combined effect, two major effects, which my research group has been looking at over the past 7 years, that combined, both of them together, seem to be suggesting that we have a major reduction in the total amount of silicate weathering that is going on the planet. Pyrite weathering on the one hand, coupled to carbonate dissolution, which releases carbon dioxide back into the atmosphere, offsetting CO2 consumption through silicate weathering, and the fact that silicate weathering was overestimated in the first place. And you take these two effects combined, and the Mekong River, which I talked about in much more detail in the first half of this talk, take those two things combined, and you find that the Mekong River doesn't consume any carbon dioxide at all. And this leaves us with a major problem. This slide was actually one of the ones which didn't show up at the beginning, and so it's nice to have it at the end. This is my picture of my volcano degassing, releasing carbon dioxide back to the atmosphere, my long-term carbon cycle. And so the question is, if the traditional view of silicate weathering over the last 40 years has been that, or the traditional view of the carbon cycle over the last 40 years has been that silicate weathering is removing that carbon dioxide from the atmosphere to stop this runaway greenhouse like we have on Venus, for example, something else must be going on. And that is where the textbooks are going to be going. The students of the future, the undergraduates of the next 10 years, they're going to be reading a textbook story which is rather different to undergraduates which have gone before. And that could be two things. It could be burial of organic carbon that plays a major role, or it could be that the chemical weathering that is, or the silicate weathering that is removing carbon dioxide is perhaps not happening on the continents at all, but is happening somewhere else. And so I think that is probably where I would like to stop at this point. I think that's about 20 minutes.
Yeah, thanks, Ed. That's perfect timing. No questions in the Q&A yet, but get typing if you'd like to ask Ed anything. I'm fascinated by, perhaps this tells you something about me, not by the geochemical diagrams, but by all the nice pictures of you intrepid people collecting samples from these vast rivers. It must be quite dangerous at times. Would you like to share one or two with us?
Yeah, I mean, I'll go back to these little videos which I put up very quickly. And where are they? Here they are. Yeah, I mean, there are certainly aspects which can be dangerous. Now, I've got to be careful what I say here, because I don't want to shoot my own fieldwork in the foot by sort of discussing safety issues. I mean, what we have are a series of fantastic adventures. Of course, I don't think it is dangerous. We wouldn't do it if it was dangerous. We couldn't do it. But what we end up having are a series of terrific adventures. You know, perhaps some of the more dangerous things or the more exotic things that we've done in our quest for understanding the sort of the global long-term carbon budget is do whitewater rafting through the Himalaya, for example. The reason being that the only way that we could access the river or the samples that we wanted to get to, it was either via helicopter, which I'm afraid we didn't have a research budget for to do that, or we were able to raft down the river and go through some sort of very exciting transect through Himalayan geology, but in a rather unusual way, in a rather fantastic way. All of these pictures that are on screen right now, these videos, these are all from the Mekong River. And you know, possibly the most spectacular one is this one up here on the upper left, which is billed as being the largest waterfall in the world, but it's the widest waterfall in the world is what it is.
Okay. We got a question from Nigel. I'm not using people's second names just because we haven't asked your permission and it's being recorded. Hello, Ed. What's your estimated global reduction in the effects of silicate weathering from the two processes you described?
Yeah, so that's work that is still in progress. We've done this for cation exchange. We have a global estimate, and our global estimate is of the order of 30% for the cation exchange process, for the second process that I talked about. For the first process, I'm still in the business of actually trying to work it out and do the research. It's quite time consuming and quite painstaking data to collect in the first place, and it's a slow task. You have to collect the samples, analyze the data, and then you have to do the modeling that goes with it. So it really is a sort of a threefold approach. In the rivers that we're looking at, it's looking like they are pretty much carbon neutral. It doesn't look like they are releasing substantial amounts of carbon dioxide back to the atmosphere. It looks like they are pretty carbon neutral overall. And so it's, in a sense, if you were to put a single number on that, that's getting on for 100% reduction in silicate weathering, or in net CO2 consumption through silicate weathering, which is really quite an extreme figure.
Thanks, Ed. So Pete's question, great presentation. Going forward, is your group going to start looking at the two questions that you highlighted? For example, silicate weathering, quote unquote, somewhere else?
Yeah, absolutely. I mean, that question was there as a cliffhanger in a sense. I mean, obviously our planetary climate hasn't been out of control. We've never become Venus, and so something that silicate weathering feedback must be happening somewhere else. And the obvious place that it's happening is actually seafloor weathering, is something that's been thought about for years, but which has been rather hard to get at. More and more people, including myself, are starting to think about the effects of seafloor weathering. Of course, the oceanic crust is a very large amount of silicate rock, basalt, which is reacting constantly with seawater through hydrothermal circulation. And I think that is probably a prime target to look at.
Thanks. And one from Stuart now. Can you comment about rates, given the need to remove large amounts of carbon from the atmosphere in a short time span? Can silicate weathering play a role in storing carbon, at least in the short term, geologically short term?
Yeah, it's a very interesting question. So the textbook view of that would be no, and would be that no, the sort of timescales of the processes which I'm talking about would be sort of acting over tens of thousands to hundreds of thousands of years, which is not much use to humans. But, and this is where there is a major but, there's a very large number of experiments going on across the planet now, where people are actually spreading silicate rock powder. In fact, some experiments going on right now near to Norfolk, where people are effectively spreading ground up basalt through sort of using tractors, using sort of fertilizer machines, spreading it all over fields and trying to measure the amount of carbon consumption there is through silicate mineral dissolution. It's called enhanced rock weathering. So they powder up the rock, they're spreading it on the land, and there is a genuine hope that this might be part of our modern climate problem. But there's a couple of major things in there. You need to know exactly what you're looking at. Any pyrite and any carbonate in there, in those rocks that you've ground up, and you're doing exactly the wrong thing. So this kind of research, which although the kind of research my group has been involved with has been, I suppose, blue skies, it may well have a planetary application in terms of removing CO2 from the atmosphere. So if you get the powder in the right format, get the rock in the right format, the rate can be fast enough.
And one final logistics one, just a more or less a one or two word answer, Ed. Where do you analyse the 10,000 samples? Back in Cambridge?
Yep. all analyses are done in Cambridge. Yet we have a lab that is a hive of activity, and PhD students, undergraduate students working around the clock to try and get through these samples. Yeah.
Right. Thanks very much. So we're going to move on to a dual effort now from Alex Copley and one of his research students, Aisling O'Kane. Alex did his undergraduate degree in Oxford, came to Cambridge to do a PhD, then went off to the States to do a postdoc in Caltech, came back to Pembroke College as a research fellow, and then moved to a lectureship and now a readership in Cambridge. He's a fellow of Robinson, looks after people there. And Aisling was trained undergraduate degree in Southampton, and then unlike the other two speakers, actually got a proper job and was an engineering geologist for 2 or 3 years, working not least on the A14, which is well known to those of us in Cambridge now, allows us at last to get out of Cambridge to the west, and we owe some of that, it seems, to Aisling and her core descriptions. And now she's doing a PhD under Alex on seismology, tectonics. Indeed, they're going to tell us what they do. Over to you two.
Great, thank you very much, Nigel. So as with Ed, and I imagine most research, this is really a sort of group effort involving sort of me, various students, various collaborators and various colleagues. And this story really starts with this map of Asia here. So as I'm sure a lot of you know, India is moving northwards about 4 centimeters per year, and it's hit Asia, and everything in between has got squashed up, and we've generated this huge swathe of mountain belts: the Himalayas, the Tibetan Plateau, the Tian Shan, the Altai, and many other mountain ranges as well. And there are lots of earthquakes as well. So all these little black dots on this map here, these are showing the locations of recent earthquakes, and these are the earthquakes that are building these mountain belts. But one of the interesting things about this whole area is how asymmetric it is. So this red line here, this divides the rocks that were originally part of India to the south and those that were originally part of Asia to the north. So you can see that India has barely deformed as part of this whole process. You know, the front edge of it's got squashed up a bit to make the Himalayas, but most of India, nothing's happened to it since it hit Asia. Asia, on the other hand, there's this huge swathe of mountain belts and earthquakes spanning thousands of kilometers northwards. So if you put these pieces of information together, you basically come to the very rough view that there's 2 kinds of continent here. There's strong continents like India, which can hit another continent and barely notice. And there are weak ones like Tibet, Asia, which if something hits them, you just get mountain ranges and earthquakes absolutely all over the place. So the question is, well, what controls, which bits are strong, which bits are weak? And what effect does this have on the whole process of mountain building, and in particular the earthquakes that happen? And this is relevant for the people who live in tectonically active places. So there's 2 main things that control the strength of rocks and the strength of minerals in rocks. One is how hot are they, and the other how wet are they. So in this sense, by wet, geologically wet, I'm meaning, is there a few % of water bound into the crystal lattices of the minerals that make up these rocks? And this has a very big effect. So this is an example from Northwest Scotland, and everything in this photograph has the same composition. It's underlyingly the same rock, but the stuff on the right here is dry, stuff on the left here is wet. The dry stuff, nothing happened to it. The wet stuff, it looks like toothpaste. And that's because it's been sheared a huge amount past this sort of rigid chunk of dry stuff. So there's this very important difference between weak and wet stuff and dry stuff which is strong. And this can give us an insight into what controls the sort of the material properties of entire continents. So this is a map of showing in red where these sort of chunks of these hard cores of these continents, where you find them. These are the strong bits. They're not really deforming regardless of what's happening around them. And these things have various geological similarities. One of the similarities is if you go and look at them, then you find that you often see similar rocks exposed to the surface at the present day. For those of you who remember your geological terminology, these are granulites. These are very high temperature metamorphic rocks. And what they tell us is at some point in the past, these rocks have been buried within mountain ranges. They got really hot, in the case of this one here from Norway, between 800 and 900 degrees. And this means that they start to melt a bit. So they partially melt. And what happens is if you start partially melting a rock, then everything that's chemically interesting, chemically exciting, all goes into the melt. And this includes water. So the water ends up in the melt. This gets extracted and then placed somewhere higher up or erupted. And it leaves behind this really dry residue. And because it's dry, it makes it strong. And you can kind of imagine this as almost analogous to toasting something. You know, you start with your nice, moist, floppy piece of bread. You toast it, you get rid of all the moisture, and you end up with your sort of dry, rigid piece of toast. So can you ever actually destroy these hard, dry bits of continent once you've created them? And the way to try and look at this is to find somewhere where you're putting something wet on top of it and trying to hydrate it again. So this is a bit of Arctic Canada here. This is from the northern corner of Quebec, where you see this little red square here. And about 2 billion years ago, this looked like the Himalayas and the Tibetan Plateau. So there's a mountain belt made of these wet, weak rocks that has been thrust over the top of one of these rigid, dry bits. So what we can do is we can look at the interface between these things, like shown on this cross section here, and see what's happening as the water is moving down from this weak, wet stuff into the hard, dry stuff. So we can look essentially along a section down here. So what we're doing here, basically the next stage in the life cycle, we're making this thing wet again and seeing what happens. And this is what this graph here is showing. So this is depth into the dry, rigid stuff underneath the mountain belt. And on the x-axis here, this is just how wet the thing is. Each one of these symbols here shows a different rock. So we've analyzed all these rocks, so we can make a picture of how the amount of water content varies as a function of depth. So how far has the water got percolating down into this rigid, dry stuff? And this line here is what you get if you go through and model all this and ask what kind of diffusivity of this water do you need to recreate these observations? And it's really small. It's 1,000 times smaller than the diffusivity of heat. And you know, we're used to things happening slowly in the geological world. This water's only got 3 kilometers in the 30 million years in which this mountain belt was active. So even by geological standards, this is incredibly slow. This means that this whole process is deeply inefficient. So basically, once you've formed one of these dry, rigid chunks of continent, it's almost impossible to destroy it. So in other words, this process of making our toast wet again doesn't really work. So once you've made these dry, rigid bits, they just stay rigid. They persist through geological time. So you can then ask what the implications of this are. So let's return then back to the modern day India-Asia collision zone. And if we draw a cross section from northern India up into southern Tibet, then it looks something like this. So this green stuff here, this is this dry, hard Indian stuff that's been thrust underneath the mountain range. And it sort of goes roughly halfway underneath the Tibetan Plateau. And it stays rigid throughout this whole distance. So the Tibetan Plateau here, it's basically like a bit of honey being dropped on a table. You know, it's wet, it's weak, it's deforming, but it's all happening above a rigid base. This is an experiment you can do for yourself at home. You put a bit of honey on the table, watch it spread out and do its own weight over time. You'll see it generates a very characteristic curving edge, and it has a flat top and a steeply sloping front. And this is actually what controls the large scale shape and size of the Tibetan Plateau. And there's a very characteristic curve along the southern edge of the mountain range. Now this big flat top plateau with this very steeply sloping front here. And this is just the result of having this rigid Indian stuff jamming underneath it. The other question we might want to ask is, well, you know, what controls the earthquake distribution in this setting? So this is this map with earthquakes on again, and things like Tibetan Plateau, it's weak, you can see there's loads of earthquakes everywhere. Actually, mostly these are relatively small. There are some exceptions, but the majority of them are fairly small. Places like India, you know, these are strong. It's very rare that you see earthquakes there, but when they do happen, they're absolutely huge. You need a big earthquake to be able to break all the way through this strong, rigid chunk of dry crust. An example of this, some of you might remember, was in northwest India in 2001, a magnitude 7 earthquake that killed a lot of people. And looking in the historical record and looking at the signs of past earthquake preserved in the landscape, when we do field work around here, we can see the whole load of magnitude 8 prehistoric earthquakes preserved here. So they're not very common, but when they do happen, they're big. So the question you might want to ask that is, well, what's happening on the interface? This sounds sort of interesting and important. What happens where you go from this weak stuff oozing out over India into the strong stuff of India itself? And this is what Ashlin's going to tell you about, looking in detail about how we understand the earthquake hazard there. So just to summarize where we've got to so far, there are these two kinds of continent, strong bits and the weak bits. You make them strong by partially melting them and sucking out the water. You can weaken them again by adding water back in, but this is slow and inefficient. So basically, once you create these things, they just persist. These strength contrasts that you make control how mountain belts work, and also the nature and the distribution of the earthquake hazard. So with that, I'm going to hand straight over to Aisling, who's going to pick up and tell you more about item 5 and how we actually go about understanding the details of the earthquake hazard on the edges of these big mountain belts.
Great, thanks Alex. So hi everyone. Now that Alex has explained what controls the shape of these foreland basins, i.e. the geological history of the basement underneath them, I'm going to follow on and show how the shape of the basins themselves at the interface controls the earthquake hazard. And this is important because big cities such as Delhi or megacities are rapidly expanding, meaning that these places are becoming more densely populated and therefore more people are exposed to the hazard from earthquakes in the adjacent mountain ranges. So starting with an example, here I show 2 images of the valley in Balakot in Pakistan. The photo on the left shows the valley before the 2005 magnitude 7 earthquake, and the photograph on the right shows the aftermath. The earthquake killed more than 80,000 people and left over 4 million people homeless. So you can see from the stark contrast between the photos that these earthquakes can cause major destruction, and it can be particularly bad where there is soft sediment, like in basins, as these are usually filled with softer soils and are known to amplify ground motions. So this is a simple diagram to refresh your memories of foreland basins. This brown material here represents the strong old cratons that Alex talked to you about. The grey material is the weaker mountains where he referred to as Tibet, and the yellow regions themselves are the soft soils and sediments. During mountain building, significant compressional stresses build up to generate faults, which are these black lines here. And over time, they stack up a bit like dominoes to make a fold thrust belt, as you can see here. This causes the crust to thicken, which increases the weight, causing the lithosphere to flex, as you can see here. I like to use this, this analogy here, where I like to think of the mountains as this big heavy weight weighing down on the crust, causing it to flex like an elastic beam or a ruler off a table. This causes the wedge-shaped basin to form, which later fills with sediment and forms a foreland basin. And an example of this is the Ganges Basin south of the Himalayas. In these continental regions, the basins are typically where people live due to the availability of water. They're flat as a pancake, so easy to build on and establish transport links. And perhaps you've even walked across one without even realizing. The Taj Mahal, for example, is built on the Ganges Basin. So now I'm going to show you how the presence of one of these basins makes a huge difference to the earthquake ground motions and therefore the seismic hazard. Here I show 2 simulations of a magnitude 6.5 earthquake, so slightly smaller than the one I showed the effects of in Pakistan, but very typical for these continental regions in the Himalayas. The top model shows the earthquake rupture through basement material, which is this old, strong cratonic material Alex talked to you about, whereas the bottom shows the earthquake rupture through cratonic material and a generic foreland basin geometry, which is made up of this weaker sedimentary material. The red lines show where the earthquake rupture originates. What you can see in both scenarios is these red and blue lines, and these represent the seismic waves. So essentially the vibrations from the earthquake. And what you can see is very different in both scenarios. In the top model, you can see the waves move across the simulation with very little interaction with the surface, whereas at the bottom model, there's a much more complex wave field because of two reasons. The first being that the waves themselves bounce back and forth off the surface and this interface, which causes a lot more vibrations and therefore a higher amplitude earthquake shaking. The second reason is due to the waves traveling through this sedimentary material into this cratonic material, which causes a lot more waves at this interface. So as you can see, there's a lot longer set of vibrations, which causes the ground shaking to last over a longer period of time. What we can tell from this then is that the earthquake shaking depends on the earthquake depth and size and the basin shape, i.e. its width and its depth. What we can do with this information then is to try and apply what we learned from our generic foreland basin geometry to a specific place, such as the Himalayas here. The Himalayas, for example, have experienced very large earthquakes in the past, with some of the largest earthquake ruptures shown by these black patches here. For example, there was a magnitude 8.2 earthquake in 1934 in Bihar, Nepal, this region here, and then an 8.6 earthquake in 1950 in Assam. And this is the largest continental earthquake ever recorded. Don't worry about these coloured bars on the figure. All you need to know is the larger the bar, the larger the potential earthquake could be. As you can see, there is some seismic gaps along the Himalayan arc in between these black rupture patches. And in a whole range of these places, you can see evidence for faulting at the surface. And these are known as fault scarps. The northwest section of the Himalayas, just up here by Jammu and Kashmir, is particularly interesting because we can't see the faulting at the surface as the fault is buried. The depth to the main fault here has been debated to be between 2 and 10 kilometers. But from our modeling, we can see that changing the earthquake depth by a small amount, even 1-2 kilometers, has a huge effect on the earthquake ground motions. So we thought it was important to study this further and better constrain the fault geometry at depth, and therefore get a better estimate of the seismic hazard. In order to do a good assessment of the hazard, we have to have a look at these places in detail. We often use satellite data to look at how fast these regions are moving and pick out features that might be interesting to investigate further in the field. We carried out fieldwork in the region in December 2019, and we looked at both the structural geology, which essentially means looking at the rock up close and personal, and we took measurements of its shape, its orientation, its current state. Here I show some dipping planes. It's basically the bedding planes have been tilted, and I've tried to outline a couple in red, so I'll just go back and forth so you can recognize those. And basically they helped us determine the overall structure of the large scale fold in the region, which is a surface expression of the faulting at depth. We also looked at the geomorphology, which for those who are unfamiliar with this term means looking at the physical features of the Earth's surface. We looked at landforms known as terraces. Again, I'll just go back and forth so you can try and recognize those. And these are just old riverbeds which have been tectonically uplifted from earthquakes and then incised from the rivers to leave behind these step-like structures. And they're typically very flat, as you can see here, and usually quite distinctive in the field. Together, looking at the geology in the field and alongside doing some geophysical analysis of past earthquakes, we can get a better estimate of the faulting at depth. This can help us then put together a time history of the deformation in the region and therefore refine our seismic hazard assessment. So in summary, Alex has shown how the geological history of the stronger cratonic material controls the shape of these foreland basins, and I've shown how the shape of the basins control the earthquake hazard. The amplitude, so essentially the amount of ground shaking from the earthquake, largely depends on its size and its depth, whereas how long the earthquake lasts, so the duration of shaking, largely depends on the foreland basin shape. A good lesson to take away from today is that on your next trip, when we can finally travel again, would be to be aware of your topography and look at the landscape around you, because whether it's a nice picturesque mountain or pan-flat topography, just think, how did it get there and what hazards they might pose? So that's all from me. So I'm happy to take any questions.
Right. Thanks very much, Alex and Aisling. There we go. Perfect timekeeping. What professionals. We've a question already. We've got a comment from Richard complimenting you on your slides, which were, I have to say, very colourful and informative. One from Nick saying, I thought Tibet was underlain by a double thickness of continental crust, the lower part being part of the Indian plate. Is this now seen as erroneous?
Not at all. That's entirely accurate. Yeah. And yeah, that idea was first actually put together in 1924 by a Swiss geologist called Emil Argand, which was a pretty impressive achievement given how far before plate tectonics it was working. But yes, this overall story of having a double thickness crust supporting the mountains, because the lower part being India and the upper part being various bits of stuff accreted to Asia, that's entirely accurate. Where the sort of subject has advanced since then, it's just this whole idea of what controls the strength of these two bits, and the fact that it's actually the bottom bit that's stronger and the top bit that's weaker, which is perhaps not what you would expect just based on things getting hotter as you go down. But which bits are wet and dry means that that's actually the other way up. So you have weak stuff on top of strong stuff. And it's understanding how that's controlling the shape of the mountain belts that you get during this doubling of the thickness of the crust is sort of really what's developed in that whole area.
Sort of relevant to that, Alex, I was wondering, given it's very difficult to hydrate crust by trying to infiltrate water downwards, would it make any difference if it was trying to get upwards from something wet put underneath it? Or is it equally difficult? Is it just the impermeability of the continental crustal rocks that's the controlling factor?
You're right that there's two ways to do it. One is the way I've talked about, and that's as sort of slow, regardless of whether you're doing it from the top or the bottom. So it's just driven by the sort of the chemical potentials. So it just goes the same speed regardless. That's just driven by the amount of water there is. But the other way you can do it is through earthquakes. So everything I was just telling you about was happening in the sort of ductile bit of the crust in terms of that hydration. But the question you got to ask is, well, if you have a great big fault cutting through it that you're getting earthquakes on, does that provide a route for fluids? And there is some suggestion that that does happen in some places, but it's also not very effective because there's only a little thin band of the sort of stuff underlying the mountain range, which is actually breaking in earthquakes. So yeah, that's not very effective because it covers a small area, and the stuff in the ductile regime is not very effective just because it goes so slowly.
Okay, thanks. No more questions in the Q&A. Just I had something I want to ask you, Ashley, which was you showed the nice model in 2 dimensions of the effect of the fallen basin on creating a greater earthquake hazard. Could you actually, if you knew the geometry of the basin in 3 dimensions very well, could you more or less turn that into an earthquake hazard map over that would be actually useful over large areas?
Yeah, so my model itself is actually 3D. I'm just showing a 2D slice. But yeah, you can, essentially it's a Cartesian grid, so you could replicate a real world example. And I did that since. I did a little slice through Jammu where we had the observations for. And essentially, yeah, you will get ground motions at a set distance that you set up your grid points in your model, and you'll get your ground velocities at every point along that. So yeah, you can get a map of the expected ground motions across that region.
Okay, thanks. Question just popped up from another Nigel. Does this new insight on relative strength of the plates change our views on the geometries of other mountain building events?
Yeah, so we're using Asia as an example, but this is all quite general in the sense that when you know what you're looking for and you're looking at other places, then yeah, you see exactly the same things. You know, Brazil going underneath the eastern side of the Andes is behaving in the same way, and you know, Arabia underneath the Zagros Mountains of Iran. So yeah, there's still some amount of sort of lateral variability that we don't fully understand. You know, why is Tibet so much higher than Iran? That kind of thing. But yeah, we are sort of starting to sort of like see these kind of effects are happening sort of everywhere we look now once you understand the underlying processes.
Good, thanks very much. So time to for me to thank the speakers and those who asked questions. We hope to run more of these events. We've been waiting to assess how successful they've been, and the number of people attending has been rewarding. So we might plan to run some more virtual talks, even if real life talks open, the potential for those opens up again. We might wait till about October. Just obviously the summer isn't the time to be dragging people off the beach to look at Zoom calls. So we'll be in touch about that. And we're just getting into gear to plan our e-newsletters in the future. And one help on great help to me on this, in fact, is going to take over the work. I want to introduce Cara Hanman, who's our new alumni coordinator. There she is. So you may or may not know that Alison, who quite a few of you got to know, our previous alumni coordinator, moved off to work with Mary Beard. I obviously don't have the charisma of Mary Beard, so she's now over in classics. I've been minding the shop for the last 7 or 8 months, but it's a great relief to have Cara as a professional to come and do it. And so expect a great increase in the quality of the communications that you get from the department. You'll be seeing more of Cara. Okay, so just remains to thank all of you for coming, and we hope you'll sign up again when we announce more opportunities. Thanks very much, everybody.